Okay, so let us begin. I'm gonna try this new way to annotate things. So one of the things that I wanted that I saw, like one of the common confusions that I saw in the group work is sort of what are all the ingredients that go into functions. So let me do this. Right, so let's talk a little bit about functions. So for a function, we have three ingredients that are all essential, right? That's why we write f from x into y, right? So the three ingredients are a set of inputs, a set of outputs, and a rule that associates outputs to inputs. Okay, it's very common in mathematics because we're lazy, right? To kind of give x and y for granted and focus exclusively on this part, on the rule, right? That's why when in calculus, you say, okay, if I give you the function f of x equals 1 over x, you should already know what the input set and the output set are. So, question for everybody. Yes or no question. So you can chat it or you can answer me. Is it correct to say that this is a function where both the input and the output set are the set of real numbers?
Yes.
Okay, I've heard a yes and I've heard some no, not in the entirety. Okay, great. So the answer, yeah, now the no's are taking the majority, and that's the correct answer, right? Because the rule, the rule 1 over x, for f to be a function from the real numbers to real numbers, should assign an output to every possible input. And if we allow 0 to be an input, right, then 1 divided by 0 is not a real number. Okay, only Chuck Norris can divide by 0, right? None of us is, right? So 0 is not an input of this function, right? So the correct statement is that 1 over x is function from the set r minus 0 to the output set being all the real numbers. Okay, so of course in calculus we do this part kind of automatically. You don't worry, just say y equals 1 over x is a function, and you automatically understand that the domain should be r minus 0, right? In this class we're going to be a little bit more careful, right? So when I ask you questions such as is the function f of x divided by x divided by 2 a function from the set of the integers to the set of the integers, right? Again, the answer is no, right? Not. Because if I take as an input 1, the output is 1/2, which is not an integer, right? So of course, if I want to fix this, I would say, okay, let's scratch this and make this output set the rational numbers, and now, yes, this is a function. Okay, so hopefully this is clarified a little bit of the confusion that I've seen before. If there's any quick question about this, let me know right away. Otherwise, I'll move on to talking about inverse image, which was the other major thing that I observed being confusing. Okay, going 1, going 2, going 3. Okay, sold. Let's move on.
What is the Q? Sorry, I'm late.
Berkeley, yeah.
What does the Q represent here? What does the Q mean?
Oh, Q are rational numbers. This is rational numbers. Which are fractions. Things of the form P over Q. Right? So 1/2 is a rational number. Yeah.
Well, how come if you're just simply, because the Z represents all whole numbers, correct?
Yes.
So then how is that not a function if you have Q in there?
So
Or am
if
I reading that wrong?
so sorry, maybe my writing made the statement confusing, right? So the function f of x equals x over 2. If you want the output set to be q, that is a function, that is good. But if you insist that the output set has to be z, then that is not a function. Right? Because the input value x equals 1 wants to have as an output 1/2, but 1/2 is not a whole number.
Oh, okay, that makes sense.
Yeah. So it's like it produces some output, but is not part of what you have decided you want the output set to be. Okay. So just, like in the first example, the one that I wrote in red, the 1 over x example, the issue was with the input set, right? That the rule that we wrote did not produce an output for every input. So we threw away the 0 and then it became a function. In the second case, the rule that we give, does not produce an output which is an integer for every input. In fact, every time you choose x to be an odd number, then the output is not an integer. So you could work on the input set and just throw away all the odd numbers, or you could change the output set and say, okay, let's allow fractions as outputs, and then it becomes a function. Okay, and Izana, I see a question. What does the column mean? You're talking about these columns right here?
Yes.
Yeah. Okay, great. So this is just a part of the notation that, F, I think of it as a rule, right? And it's a rule, and this notation, column X, arrow Y, is a notation that is used to say it's a rule that assigns to elements of the input set X, elements of the output set Y. And it's just, yeah, I don't think I have any better answer than this. It's just this sort of standard notation. It's sort
Okay,
of, Colin is like, I'm going to explain to you what the input and the output set for F are. So that's why F column X to Y.
Okay. I just didn't know how to read it as I was reading that notation, but
yeah. So I would read it as F is a function from X to Y, or F from X to Y.
Okay.
That's how to read it.
Cool.
Great. Thank you very much for the questions, Berkeley and Izana. So I'm going to wipe this board clean and start again. Okay, let's talk about inverse. And before we say anything too formal about this, so the concept of inverse image is very closely related to solving equations. Why? Because, okay, let's do something that you've all known how to do since high school or even earlier, right? So if I give you the equation x squared equals 4, right? None of you has a problem to saying that it has solutions x equals plus or minus 2. Okay, it's an equation of second degree, and it has two solutions. Okay, but now I want to interpret what we just did in terms of functions, right? And so I want to interpret it as follows. I say, so we have a function, the function y equals x squared. And we want to know what are the inputs such that the output is equal to 4. Right? This is what it means to solve the equation x squared equals 4, right? Because we're basically saying, let's let y equal 4. And then let's ask ourselves, what are the x's for which the output for that x is exactly 4? So if we call this function f, right? So our new language to describe this situation is that the inverse image of the element 4 is the set consisting of two elements, plus or minus 2. Okay? So now we're thinking of 4 as a one-element subset. And notice that this f inverse is not a function that takes as input y values and produce x values, because the one-element subset 4, that you could think of it as a y input, produces two outputs, right? So it produces a subset. Okay. Also, if we think about what's happening in the language of kind of Calc 1, so my inputs live on the x-axis, my output lives on the y-axis, and I can identify the function y equals x squared with its graphs, and so I get this parabola. Okay, so finding the inverse function, sorry, so not the inverse function. The inverse function doesn't exist. Finding the inverse image of the element 4, right, consists in looking at what are the input values, what are the x points that y equals x squared assigns to the output 4. Okay, and so now, of course, we might, for example, not be interested in just knowing what's the solution of the equation x squared equals 4, but we might, want to know, okay, what if I just want to fall in the interval between 4 and 5? Because, well, maybe I want to have an acceptable range of solutions, right? And then, of course, the answer to this problem is that there's going to be two intervals on the x-axis, right? From 2 to square root of 5, and from minus square root of 5 to 2. And these two intervals are the inverse image of the set the interval from 4 to 5 in the y values.
So what, hang on, I'm sorry, I'm trying to think. How does, or I guess what is the definition of an inverse image? Like,
So it's on the book. So let me pull it out for a second if I can. I have to do this. And I have to pull out the book. You guys can all see it, right? So it's here. It's definition 6.6. Okay. Let me highlight it. So if we have a function, right, such that the input set is x, the output set is y, and you start with a u, which is a subset of y, right? Then the inverse image of u is a subset of x. And how is this subset of x defined? It consists of all the elements of x whose output via f is an element of u, right? So the short and confusing math way to write this is this one. F inverse u is the set of x in x such that f of x is in u. Okay? But if I now go back to my screen here, right? So in this case, in this particular example that I drew, this interval is my set u, right? Is maybe the interval from 4 to 5, and it's a subset of the y-axis, right? And then the inverse image consists of these two intervals right here. It's a subset of the x-axis of all the points on the x-axis that the function maps to the interval on the y-axis that we started from. Okay, and I just saw Tyler's question as well. And this in particular, so let me again go back real quick to the definition. If we choose, in fact, let me wipe this off for a second. It's really small. Okay, so if we choose U to be the empty set, right? How does this definition now read? So the inverse image of the empty set, which is denoted as F inverse of the empty set, is the subset of all elements of X whose output via F belongs to the empty set, right? So F inverse of the empty set is the set of all X in X such that F of X is an element of the empty set. But the empty set has no elements. Which implies that no X in X satisfies this condition. Which implies, well, that F inverse of the empty set has no elements, and so is the empty set. Cool. Everybody happy with this?
I have a quick weird question.
Yeah, quick weird questions are great.
I know empty sets are very weird, but would it be possible to have an empty set inside of an empty set?
So first of all, there's only one empty set, right? So and the empty set is a subset of any set, including being a subset of itself. So this is, yeah, it's very weird. But I mean, you know, the empty set is just a set that has no elements. So it doesn't have it doesn't live physically anywhere, right? So that's, yeah, I mean, it's a little weird because, you know, we like to think of, you know, sets as, you know, we draw bubbles, right? And we think of elements in here. and you say, okay, well, maybe here's an empty set because I have no elements of x in here, but here's another empty set where there's no elements, and these are different empty set because I drew them in different places. But that's not really the case. I mean, there's just one empty set, which is a set with no elements, which just happens to, you know, be a subset of whatever you want it to be. That's the case.
Yeah.
So
I guess my question was going to lead to whether if an inverse image of an empty set would be an empty set.
yes. Right? So if we just follow the definition here that is still sketched on the page of the book that's right here, right? The inverse image of the empty set is the set of elements of x such that f of x is in the empty set, right? But because f of x is an element of y, so it is an element, right? So it's not, f of x is not contained in the empty set for any x. So there is no elements in f inverse of the empty set, and so f inverse of the empty set is itself the empty set.
Okay.
Does that help?
Yes. Well, just one more question on that. If we were able to say, like, if an empty set is an element of an empty set, which was kind of like my first question.
So empty set, so sets are not elements, right? In general, right? So the empty set is just the empty set,
Mm-hmm.
right? And the empty set has no elements, right? So if you were to think the empty set as the element of another empty set, then that empty set would have an element and would not be empty anymore.
Yeah.
Right? So yeah.
Okay. Okay. Makes sense. Cool.
Cool. Great. Yeah, these are, I mean, empty sets are forever confusing, and yeah, c'est la vie.
So kind of on the empty set, where it says no x satisfies, like the inverse image of the empty set, why wouldn't some x that's answer is 0 satisfy?
Well, zero is not, zero is an element, right? It's not.
Okay.
Right? The empty set is not zero. The empty set is like vacuum. There's nothing in there. Okay, again, sometimes we get the confusion going, but the empty set is something that has no elements. Okay, so let me draw another kind of silly picture here real quick. Maybe just to back here, wipe, and let's go with our usual x and y, and I have a function f. I'm going to define by giving a few arrows here. Here, okay. So x has 4 elements maybe. And y has 5 elements. Okay. And again, one way that you can represent the empty set if you want in this picture is saying, okay, let me just take something, a little region, which doesn't contain any element of y. And now your question is like, what are the elements of x that fall inside this region? Well, there's none of them, right? So that's why the f inverse of the empty set is the empty set. It is possible that there's other sets whose inverse image is the empty set, right? So if I take as a set this one to be my u, right? Then f inverse of u is also the empty set. right? Because there's no elements of X that F maps to U, to elements of U.
So that first like function that's written out in red, where it says F inverse of the empty set equals the empty set.
Okay, so sorry, let me stop you right away. This is not a function, right? This is an equality of sets. It's an equality of subsets of X.
So the equality, is that kind of saying that like the inverse image of the empty set is the empty set?
That's correct. That's correct. This is precisely the statement. The inverse image of the empty set is the empty set.
So by similar logic, could we draw another little yellow empty set in the X?
Yeah, just like I was telling Izana, it doesn't really matter. The empty set doesn't really live anywhere in particular. It's just a set with no elements, which happens to be a subset of any set you want, right? But yes, I can definitely.
So if there was a line drawn, it would be going in between the two empty sets.
Well, except there can be no elements in these yellow dots, so there can be no arrows starting from that one to the other.
Okay.
Cool. Does that help? All right. Izana, you have another question? You want to jump in?
Yes. I've noticed that we've been talking about inverse images only for sets, I guess, like the U set. So my question is, would there be what would be the problem of saying what is the inverse image of a specific element of Y rather than a set?
Yeah. So that's a very good question. There's no problem in saying what is the inverse image of an element of Y. But the problem, if you think of it, that the inverse image of an element of Y should be an element of X. Okay? And it is not, or it's not necessarily, right? Because let me show some examples here in the picture, right? If I take as an element of Y this one that I just circled in blue, then its inverse image is in the empty set, right? On the other hand, if I take, let me find another color that I haven't used. Well, I ran out of colors in this palette. Let me take black here. And if I take the inverse image of this element, then this inverse image consists of two elements of X, right? So it consists of a set of elements, a subset of X, okay?
Okay.
So the correct statement is that, okay, so let me write it here, that's important. So the correct statement is that the inverse image is not a function from X to Y. Sorry, is not, so let me write something wrong first. So the inverse image is not a function for Y to X, okay, because it does not assign to elements of Y elements of X, right? The correct statement, if you want to think of the inverse image as a function, is that the inverse image assigns two subsets of Y subsets of X. Okay? And so in particular, among the subset of Y, you can take single element subsets, that's fine. This is sort of the same as taking elements of Y, but the outputs are not necessarily elements of X, they're subsets of X. That could be the empty set, they could have a lot of, elements and so on and so forth.
Okay. Okay, that makes perfect sense. Thank you.
Is that okay? Great, great. So let me. I wanted. What symbol is that? Which one? The P?
Yeah, that one.
Yeah. So this one. Let me explain this. The P of X is the symbol that we use for the power set of X, which is defined to be the set of all subsets of X.
Okay.
So let me do a quick example. I need to wipe this board. So if X is the set 1, 2, right, then P of X has 4 elements, the empty set, the single element subset 1, the single element subset 2, and the set 1, 2. And actually, let's play this game real quick. Let me call this Y instead of X. And let's suppose we have a function from X to Y, call this F, and X has A, B, C, 3 elements, and my F is the constant function 1, right? Then F inverse, like I said, is a function from subsets of Y to subsets of X. So it can take as inputs the empty set, the singleton 1, the singleton 2, and the set 1, 2. And the outputs are the empty set, all of X, the empty set, all of X.
Okay, and this is pretty much what we're doing on problem 6.4 in the group work, correct?
Yes, yes,
Okay.
that's problem 6.4. And I just noticed on the chat there's a great observation by Nathan, and I point it out here. Oops. Oh, chat is not okay. It's right here. So if F is a bijection, and only if F is a bijection, then when I look at this function F inverse from Py to Px, and I just evaluate it, I just allow as inputs the single element subsets of Y, and I think of them as elements of Y, I get as output single element subset of X, which I can think of as element of X, and therefore I have what's called an inverse function from Y to X. Exists. Right? This is why this whole inverse image thing is so confusing, because we're often used to the inverse function before we start thinking about more subtle things, right? And f inverse typically is not a function for y to x, but it is in the special case where when f is bijective, is a bijection.
So just to recap what you said.
Yeah.
The comparison of the two sets, that the A, B, and C all go to the inverse image, or like the I guess the inverse function f of x does not exist.
Sorry, what?
If the function f of x equals y, that we have up at the top with the two circles and A, B, C, 1, 2.
Yeah.
Yes. If is a function.
Yeah, so this is a function. This whole picture represents a function.
But the inverse of that is not a function.
So the inverse of that is not a function from y to x. It's a function from the power set of y to the power set of x, right? So if you give me as input a subset of y, right, then you can produce as output a subset of x.
Okay.
Right, but it's not a function from y to x, because if you just say, okay, if I just look at the element 2, the inverse image is empty. There's nothing here, right? So that's not an element of x. On the other hand, if I look at the element 1, then its inverse image is all of x is a, b, and c. So it's not one element of x, it's 3 elements of x, right? So that's not a function from y to x, because a function needs to always have unique outputs. And so the solution is say, okay, well, but we did construct something with this procedure, but the thing that we construct is an element of the power set of x, is a subset of x, is not an element of x. So this is, it's subtle and confusing, but I think that once we become friends, then it'll be okay. Okay, so I wanted to do a silly example, a silly motivational example as to why we care. So we care, like I said earlier, like we care about inverse images because, we care about solving equations or inequalities, and we care solving equation or inequalities because a lot of us, are scientists, and scientists perform experiments, and sometimes you want your output of an experiment to fall within a certain range, right? And then you want to know, how do you control the inputs, right? So here's a stupid example, right? Suppose that you're a circus director, right? And you're gonna, or you're a circus acrobat, one of those that get shot from the cannon, right, in the air. There you go. That's you, right? And you would like to make sure that when you're landing, you land into the protective net that catches you, right? So it's here, right? So the idea is that, okay, so we have a function where maybe the input is the angle at which you orient the cannon. And the function output we call it d of theta, right, is the distance that you travel flying if you're shot from angle theta, right? So for example, if I give you d of pi halves, that's 0, because if theta is pi halves, then you get shot straight vertically up, and then you fall right back inside the cannon. Don't do it at home, not very productive, right? But then your question is, okay, well, I mean, you have a net that will span the distance between two values, dA and dB, right? And you want to make sure that you land in here, right? So what you want is you want to find the inverse of dA dB. And this is the, what's the interpretation of this inverse image, right? So is the range of angles that you're shot at that makes you land into the net. They make you land. Okay, so now this is of course a very, very silly example, right? But you can sort of like adapt this to whatever is the branch of science that you're most interested in, right? And you can imagine that you have an experiment that depends in a certain way upon like some way that you choose your inputs and will produce certain outputs, and you have a certain range of outputs that you are looking for because you want to land your rocket on the moon, because you want to bake your cake in such a way that it rises enough, but it doesn't taste like baking soda, and so you want to have a certain range of the amount of baking soda that you put in the cake. You name it, right? Come up with whatever like scientific experiment you want, where you want to say, I want to find what is the range of inputs that will guarantee that I have an acceptable range of outputs. When you're doing that, you're finding the inverse image of a set of outputs. Cool. So everybody happy? I'm guessing silence means yes. Okay, thanks, Susanna and Heidi. Right. So at this point, that's all I wanted to say, but let me quickly scroll through the group work problems. And if anybody has some other questions that you want to ask, please do it soon.
Can we talk about the last group work problem?
Yeah, okay. Oh, yes. Let's do that. Absolutely. Great. Let me pull out again to draw. Like this. This. Okay, so we're now in the situation where we have two functions, right? We have a function f from x to y, we have a function g from y to z, and we have a function g composed with f from x to z, right? And we have two subsets of X. One is the inverse image via the function G composed with F of a subset U. And the other is the inverse image via F of the inverse image via G of U. Okay, so let's think about what we're trying to do, right? So we start from a set U in here. And in this first case, we're saying what are all the elements of X that this function right here sends immediately inside U. Okay, so that's this set. So you have elements of X that end up in elements of U. Whereas maybe you have some other elements of X that via this function end up inside U. The other set, this one, well, again, you start from U and you say, okay, let's first find the elements of Y that G maps inside U.
A very nice happy clown you've drawn, Renzo.
Yes. And then let's find the element of X that F maps inside this kind of pink blob, G inverse of U. Right? And so the idea is you're looking for elements of X that are going to end up in U in two different ways, either in one fell swoop through the arrow downstairs, or in two steps by first mapping to this orange intermediate blob and then mapping to U. And how do you prove formally that these two sets are the same? Well, you say, okay, what is the definition of G composed with F inverse of U? Well, this is the set of X in X such that G composed with F of X is in U. Okay, but then let's see what is the definition of this set. Well, these are the X in X, because this is first of F inverse of G inverse of U, right? So this is the X in X such that F of X is in G inverse of U. But what does it mean to be in G inverse of U? Well, it means that so F of X is in G inverse of U if G of F of X is in U. But by definition, G of F of X is G composed with F of F. So now this is equal to this. Okay, so the way that you prove this equality, right, is just by writing down the definition of what it means to be an element of the inverse image of G composed with F of U, and what it means to be an element of F inverse of G inverse of U. And then you have to sort of manipulate, because this is in two steps, right? The first definition is not quite unraveled completely. You have to, re-express it in an equivalent way here. And then once you re-express it this way, you see that this is equal to this one up here. Simply by definition, G composed with F of X by definition is G of F of X. Okay. Hopefully that helped. Great. Time's up. Time flies when you're having fun. Thank you all guys for attending. I would encourage you, like usual, as usual, to send me questions, and if you need to meet, I'm happy to have office hours. Upon your request. Even better if a group of you will want to meet, and then we can organize it that way. All right. Thank you all very much, and see you all on Tuesday or before. Stay safe and stay sane. We're all doing our best. Okay. Bye, everybody.